Rendering is the process of generating an image from a 2D or 3D model, by means of computer programs. Also, the results of such a model can be called a rendering. A scene file contains objects in a strictly defined language or data structure. It would contain geometry, viewpoint, texture, lighting, and shading information as a description of the virtual scene. The data contained in the scene file is then passed to a rendering program to be processed and output to a digital image or raster graphics image file. The term rendering may be by analogy with an artist's rendering of a scene, though the technical details of rendering methods vary. The general challenges to overcome in producing a 2D image from a 3D representation stored in a scene file are outlined as the graphics pipeline along a rendering device, such as a GPU. A GPU is a purpose-built device able to assist a CPU in performing complex rendering calculations. If a scene is to look relatively realistic and predictable under virtual lighting, the rendering software should solve the rendering equation. The rendering equation doesn't account for all lighting phenomena, but is a general lighting model for computer-generated imagery. Rendering is also used to describe the process of calculating effects in a video editing program to produce final video output. Rendering is one of the major subtopics of 3D computer graphics, and in practice is always connected to the others. In the graphics pipeline, it is the last major step, giving the final appearance to the models and animation. With the increasing sophistication of computer graphics since the 1970s, it has become a more distinct subject. Rendering has uses in architecture, video games, simulators, movie or TV visual effects, and design visualization, each employing a different balance of features and techniques. As a product, a wide variety of renderers are available. Some are integrated into larger modeling and animation packages, some are standalone, some are free open-source projects. On the inside, a renderer is a carefully engineered program, based on a selective mixture of disciplines related to light physics, visual perception, mathematics and software development. In the case of 3D graphics, a rendering may be done slowly, as in pre-rendering, or in real time. Pre-rendering is a computationally intensive process that is typically used for movie creation, while real-time rendering is often done for 3D video games which rely on the use of graphics cards with 3D hardware accelerators. Usage. When the pre-image is complete, a rendering is used, which adds in bitmap textures or procedural textures, lights, bump mapping and relative position to other objects. The result is a completed image the consumer or intended viewer sees. For movie animations, several images must be rendered and stitched together in a program capable of making an animation of this sort. Most 3D image editing programs can do this. Features. A rendered image can be understood in terms of a number of visible features. Rendering research and development has been largely motivated by finding ways to simulate these efficiently. Some relate directly to particular algorithms and techniques, while others are produced together. Shading, how the color and brightness of a surface varies with lighting. Texture mapping, a method of applying detail to surfaces. Bump mapping, a method of simulating small-scale bumpiness on surfaces. Fogging, participating medium, how light dims when passing through non-clear atmosphere or air. Shadows, the effect of obstructing light. Soft shadows, varying darkness caused by partially obscured light sources. Reflection, mirror-like or highly glossy reflection. Transparency, transparency or opacity, sharp transmission of light through solid objects. Translucency, highly scattered transmission of light through solid objects. Refraction, bending of light associated with transparency. Diffraction, bending, spreading and interference of light passing by an object or aperture that disrupts the ray. Indirect illumination, surfaces illuminated by light reflected off other surfaces, rather than directly from a light source. Caustics, reflection of light off a shiny object, or focusing of light through a transparent object, to produce bright highlights on another object. Depth of field, objects appear blurry or out of focus when too far in front of or behind the object in focus. Motion blur, objects appear blurry due to high-speed motion, or the motion of the camera. Non-photorealistic rendering, a rendering of scenes in an artistic style, intended to look like a painting or drawing. Techniques. Many rendering algorithms have been researched, and software used for rendering may employ a number of different techniques to obtain the final image. Tracing every particle of light in a scene is nearly always completely impractical and would take a stupendous amount of time. Even tracing a portion large enough to produce an image takes an inordinate amount of time if the sampling is not intelligently restricted. Therefore, a few loose families of more efficient light transport modeling techniques have emerged. Rasterization, including scanline rendering, geometrically projects objects in the scene to an image plane, without advanced optical effects. Raycasting considers the scene as observed from a specific point of view, calculating the observed image based only on geometry and very basic optical laws of reflection intensity, and perhaps using Monte Carlo techniques to reduce artifacts. Raytracing is similar to raycasting, but employs more advanced optical simulation, and usually uses Monte Carlo techniques to obtain more realistic results at a speed that is often orders of magnitude slower. The fourth type of light transport technique, radiosity, is not usually implemented as a rendering technique, but instead calculates the passage of light as it leaves the light source and illuminates surfaces. These surfaces are usually rendered to the display using one of the other three techniques. Most advanced software combines two or more of the techniques to obtain good enough results at reasonable cost. Another distinction is between image order algorithms, which iterate over pixels of the image plane, and object order algorithms, which iterate over objects in the scene. Generally, object order is more efficient, as there are usually fewer objects in a scene than pixels. Scanline rendering and rasterization. A high-level representation of an image necessarily contains elements in a different domain from pixels. These elements are referred to as primitives. In a schematic drawing, for instance, line segments and curves might be primitives. In a graphical user interface, windows and buttons might be the primitives. In rendering of 3D models, triangles and polygons in space might be primitives. If a pixel-by-pixel approach to rendering is impractical or too slow for some task, then a primitive-by-primitive approach to rendering may prove useful. Here, one loops through each of the primitives, determines which pixels in the image it affects, and modifies those pixels accordingly. This is called rasterization, and is the rendering method used by all current graphics cards. Rasterization is frequently faster than pixel-by-pixel rendering. First, large areas of the image may be empty of primitives. Rasterization will ignore these areas, but pixel-by-pixel rendering must pass through them. Second, rasterization can improve cache coherency and reduce redundant work by taking advantage of the fact that the pixels occupied by a single primitive tend to be contiguous in the image. For these reasons, rasterization is usually the approach of choice when interactive rendering is required. However, the pixel-by-pixel approach can often produce higher quality images and is more versatile because it does not depend on as many assumptions about the image as rasterization. The older form of rasterization is characterized by rendering an entire face as a single color. Alternatively, rasterization can be done in a more complicated manner by first rendering the vertices of a face and then rendering the pixels of that face as a blending of the vertex colors. This version of rasterization has overtaken the old method as it allows the graphics to flow without complicated textures. This newer method of rasterization utilizes the graphics card's more taxing shading functions and still achieves better performance because the simpler textures stored in memory use less space. Sometimes designers will use one rasterization method on some faces and the other method on others based on the angle at which that face meets other joined faces, thus increasing speed and not hurting the overall effect. Raycasting. In raycasting, the geometry which has been modeled is passed pixel by pixel, line by line, from the point of view outward, as if casting rays out from the point of view where an object is intersected. The color value at the point may be evaluated using several methods. In the simplest, the color value of the object at the point of intersection becomes the value of that pixel. The color may be determined from a texture map. A more sophisticated method is to modify the color value by an illumination factor, but without calculating the relationship to a simulated light source. To reduce artifacts, a number of rays in slightly different directions may be averaged. Rough simulations of optical properties may be additionally employed. A simple calculation of the ray from the object to the point of view is made. Another calculation is made of the angle of incidence of light rays from the light source, and from these, as well as the specified intensities of the light sources, the value of the pixel is calculated. Another simulation uses illumination plotted from a radiosity algorithm, or a combination of these two. Raycasting is primarily used for real-time simulations, such as those used in 3D computer games and cartoon animations, where detail is not important, or where it is more efficient to manually fake the details in order to obtain better performance in the computational stage. This is usually the case when a large number of frames need to be animated. The resulting surfaces have a characteristic, flat, appearance when no additional tricks are used, as if objects in the scene were all painted with matte finish. Raytracing. Raytracing aims to simulate the natural flow of light, interpreted as particles. Often, raytracing methods are utilized to approximate the solution to the rendering equation by applying Monte Carlo methods to it. Some of the most used methods are path tracing, bidirectional path tracing, or metropolis light transport. But also semi-realistic methods are in use, like weighted-style ray tracing, or hybrids. While most implementations let light propagate on straight lines, applications exist to simulate relativistic spacetime effects. In a final, production-quality rendering of a ray-traced work, multiple rays are generally shot for each pixel, and traced not just to the first object of intersection, but rather, through a number of sequential bounces, using the known laws of optics such as angle of incidence equals angle of reflection, and more advanced laws that deal with refraction and surface roughness. Once the ray either encounters a light source, or more probably once a set limiting number of bounces has been evaluated, then the surface illumination at that final point is evaluated using techniques described above, and the changes along the way through the various bounces evaluated to estimate a value observed at the point of view. This is all repeated for each sample, for each pixel. In distribution ray tracing, at each point of intersection, multiple rays may be spawned. In path tracing, however, only a single ray or none is fired at each intersection, utilizing the statistical nature of Monte Carlo experiments. As a brute force method, ray tracing has been too slow to consider for real time, and until recently too slow even to consider for short films of any degree of quality, although it has been used for special effects sequences, and in advertising, where a short portion of high-quality footage is required. However, efforts at optimizing to reduce the number of calculations needed in portions of a work where detail is not high or does not depend on ray tracing features have led to a realistic possibility of wider use of ray tracing. There is now some hardware-accelerated ray tracing equipment, at least in prototype phase, and some game demos which show use of real-time software or hardware ray tracing. Radiosity. Radiosity is a method which attempts to simulate the way in which directly illuminated surfaces act as indirect light sources that illuminate other surfaces. This produces more realistic shading and seems to better capture the ambience of an indoor scene. A classic example is the way that shadows hug the corners of rooms. The optical basis of the simulation is that some diffused light from a given point on a given surface is reflected in a large spectrum of directions, and illuminates the area around it. The simulation technique may vary in complexity. Many renderings have a very rough estimate of radiosity, simply illuminating an entire scene very slightly with a factor known as ambience. However, when advanced radiosity estimation is coupled with a high-quality ray tracing algorithm, images may exhibit convincing realism, particularly for indoor scenes. In advanced radiosity simulation, recursive, finite element algorithms bounce light back and forth between surfaces in the model, until some recursion limit is reached. The coloring of one surface in this way influences the coloring of a neighboring surface, and vice versa. The resulting values of illumination throughout the model are stored and used as additional inputs when performing calculations in a raycasting or raytracing model. Due to the iterative, recursive nature of the technique, complex objects are particularly slow to emulate. Prior to the standardization of rapid radiosity calculation, some graphic artists used a technique referred to loosely as false radiosity by darkening areas of texture maps corresponding to corners, joints and recesses, and applying them via self-illumination or diffuse mapping for scanline rendering. Even now, advanced radiosity calculations may be reserved for calculating the ambience of the room, from the light reflecting off walls, floor and ceiling, without examining the contribution that complex objects make to the radiosity, or complex objects may be replaced in the radiosity calculation with simpler objects of similar size and texture. Radiosity calculations are viewpoint independent, which increases the computations involved, but makes them useful for all viewpoints. If there is little rearrangement of radiosity objects in the scene, the same radiosity data may be reused for a number of frames, making radiosity an effective way to improve on the flatness of raycasting, without seriously impacting the overall rendering time per frame. Because of this, radiosity is a prime component of leading real-time rendering methods, and has been used from beginning to end to create a large number of well-known recent feature-length animated 3D cartoon films. Sampling and filtering. One problem that any rendering system must deal with, no matter which approach it takes, is the sampling problem. Essentially, the rendering process tries to depict a continuous function from image space to colors by using a finite number of pixels. As a consequence of the Nyquist-Shannon sampling theorem, any spatial waveform that can be displayed must consist of at least 2 pixels, which is proportional to image resolution. In simpler terms, this expresses the idea that an image cannot display details, peaks or troughs in color or intensity that are smaller than 1 pixel. If a naive rendering algorithm is used without any filtering, high frequencies in the image function will cause ugly aliasing to be present in the final image. Aliasing typically manifests itself as jaggies, or jagged edges on objects where the pixel grid is visible. In order to remove aliasing, all rendering algorithms must use some kind of low-pass filter on the image function to remove high frequencies, a process called anti-aliasing. Optimization. Optimizations used by an artist when a scene is being developed due to the large number of calculations. A work in progress is usually only rendered in detail appropriate to the portion of the work being developed at a given time. So in the initial stages of modeling, wireframe and raycasting may be used, even where the target output is ray tracing with radiosity. It is also common to render only parts of the scene at high detail, and to remove objects that are not important to what is currently being developed. Common optimizations for real-time rendering. For real-time, it is appropriate to simplify one or more common approximations. and tuned to the exact parameters of the scenery in question, which is also tuned to the agreed parameters to get the most bang for the buck.